And there's a well-known trend in the solar system that lower mass planets have more metal-rich atmospheres. And I know there are some physicists in the audience, so by metal I mean water. I see, yeah, I wrote water there. Okay, so, so we see this trend. There's a question, why is this there? You can make up some theories that are physically motivated for why this might be, depending on how efficient you are as a forming planet in accreting gas versus rocks and ice. But we don't know whether this is universally true or this is just something that happens to be the case in the solar system. And the advantage of exoplanets is that we have a huge sample size to draw on. And so one planet that I've worked on in great detail is WASP-43b. This is a hot Jupiter. Hot Jupiters are great for studying chemical abundances because they're so hot that the key molecular species are well mixed, and in the gas phase you can see them. By contrast, on Jupiter it's so cold that the water has frozen out of the observable part of the atmosphere. So I measured the spectra of this hot Jupiter, both the thermal emission spectrum and also the transmission spectrum. In both cases you can see clear absorption features from water centered at 1.4 microns. Just a reminder, absorption is up for transmission spectroscopy because when the atmosphere is more opaque, the planet looks bigger. And based on these data, we retrieved the water volume mixing ratio in the atmosphere. We marginalized over possible temperature structures, possible chemical compositions, and we ended up with a mixing ratio of about 200 to 3,000 parts per million. Now, I'm calling this very precise. I know that not everyone in the audience thinks that this is precise, but to put it in context, this is about 100 times more precise of a measurement than had been obtained before. And importantly, it's good enough to start putting exoplanets on this plot. So here's where WASP-43b falls, beautifully in line with the solar system trend. Now, I would not make any claims about having solved planet formation from this single measurement, but I think that the key point is that this is a proof of concept that it's possible to make this type of precise abundance measurement for exoplanets, and this really motivated measurements like this for a bigger sample, and already we can see that this simple picture of a power law is not right. And going forward, towards the end of my talk, I'll talk about a mission recently selected by ESA that is going to do this type of measurement for a sample of 500 to 1,000 planets. Okay, so a second frontier is, I call this one in my head, this planets are round. We forget about this sometimes because we can't actually see them, but it's really important, particularly for planets that are tidally locked, so they have a really hot side and a really cold side. We don't expect, certainly the temperature or the chemistry to be the same everywhere. And so the question is, how well can we determine the 3D temperature, structure, and chemical composition for an exoplanet? Here's another of my results. I observed thermal phase curves for an ultra-hot Jupiter. This is even hotter than the last one, so my nickname for this planet is habanero. Yeah, you laugh, but you'll remember. So we observed it with Hubble and with Spitzer. Here are the data on the left. You can see it looks just like the cartoon. This is the hot dayside rotating into view. Here's the planet getting eclipsed by the host star. And we use this to make a temperature map of the planet. And you can see a huge temperature contrast from the day side to the night side, about 2,000 Kelvin temperature difference. The steepness of that temperature gradient shows us that the heat is being re-radiated back into space much faster than it can circulate by wind. And that is matches well with predictions from 3D models of the atmosphere. We can also deconvolve this into spectra from different regions of the planet's atmosphere. So this on the top right is what the spectrum of the planet's day side looks like. Here's the spectrum of the planet's night side. a couple, I guess maybe the most important thing to note is this point I've circled in red. And it's a little hard to see here, but on the day side, that point is higher than the black body curve shown in blue. And on the night side, it's colder. And what we inferred from this is that there's actually a temperature inversion on the planet's day side. So that 4.5 micron point corresponds to a CO band. And on the day side, if you look in that higher opacity band, you're seeing higher up in the atmosphere, but it's hotter up there. And this is exactly what is expected if you're heating up your atmosphere from the star. But on the night side, that heat source is gone. And so the thermal inversion goes away. And this is the first time we've seen a change in the temperature structure of a planet between the day side and the night side. Clouds. Okay, we know that all of the planets in the solar system that have substantial atmospheres also have clouds or haze. The way that clouds would manifest in the spectrum of an exoplanet is that they truncate your spectral features. So if you can imagine the starlight filtering through the terminator of the planet, it gets blocked by clouds at high altitude. And so instead of observing a spectrum with big features like this, you might observe just a tiny spectral feature poking out above the clouds. One of the discoveries I'm most proud of is a very definitive detection of clouds or haze on GJ1214b, a 2.7 Earth radius planet, discovered by our very own Professor Charbonneau. And what we found is that the spectrum is so flat that even if the atmospheric composition is highly molecular weight, made entirely of water or methane or even CO2, which is very heavy, none of those models match with the data. The spectrum is too flat, and therefore there must be clouds or haze in the atmosphere that are truncating the amplitude of the spectrum. And so the question immediately arises, what kinds of clouds are these? So this planet is about 500 Kelvin, so it's too hot for water clouds to condense. At these temperatures, you would expect thermochemical equilibrium clouds made out of salts and sulfides. You can also get photochemical hazes produced by methane photolysis that then recombines into soots, higher order hydrocarbons. And so this is the retrieved cloud top pressure as a function of the atmospheric composition, so more hydrogen rich over here, more water rich over here. And you can see that for any composition, the clouds have to be above about 1/10 of a millibar altitude, which is totally crazy because Earth clouds are all the way down here. So not only do these clouds have to be made out of a different kind of material, they're also forming in a really different place. An update on this. So after this result came out, everyone got really worried and they said, what if all of these small planets have clouds? And the clouds are interesting in their own right, but if you want to see into the atmosphere and figure out what it's made out of, the clouds are in the way. And so over the last 5 years or so, we've been working really hard to build up a bigger sample of these small planets. And as a card-carrying astronomer, when you have a sample size of 6, that's enough to start doing a demographic study. So that's what I'm showing here. These are the spectra of all of the Neptune-sized planets that have been observed so far. This is all Hubble data. And we found a tentative trend in the amplitude of spectral features with the temperature of the planet. And that makes some sense because at lower temperatures you can have more molecules condensing. In particular, below about 800 Kelvin, methane is the dominant carrier of carbon. And so it's really good at making these thick photochemical soot hazes. But I would not venture to say that a sample size of 6 is enough to really solve this question. And so one thing I've been pushing on really hard is to get more spectra of these small planets. So we have 4 more coming from a program that's ongoing. We've also seen in some cases that the properties of the clouds can be determined quite well. So this is the transmission spectrum of DJ3470b. This is a Neptune-sized planet. And you can see right here, there's a little tiny water feature poking out above some clouds. And the idea I had is to also study the planet farther into the infrared, because we expect the optical properties of the clouds to change with wavelength. And indeed, if you go over here to Spitzer wavelengths, and this is data from a program of mine, you can see that there's a big difference from the near infrared to the infrared, and you can also see a change in the size of the planet here in this CO2-CO band. And the best explanation for this at the moment is we think that the particles are fairly small, so about half a micron in size, and that their opacity drops off really steeply beyond about 2 microns. And so this is an exciting find for JWST where we'll have access to the longer wavelengths. Okay, I'm really excited about this one, so I'm going to spend a little bit more time talking about it. So there's a lot of talk about biosignatures in the atmospheres of terrestrial planets. But there are some zeroth order questions that we need to address first, I think, before we get to there. So a big one is, do terrestrial planets have atmospheres or not? How often, under what conditions? From our